So welcome to the Vapor class. So today the session number 3. Today we are going to study about the surface stress charge regime and the threshold voltage. So in the previous class we studied about the MIS structure, that is the MIS stands for metal insulator semiconductor, that is MIS diode we see. Then in that we studied about some of the three categories of operation we studied. The one is the accumulation, the second one is depletion, the third one is inversion. Then then we studied something about over there actually in the with the help of a energy band diagram. Now with the continuation of that, so now what we are going to do, we are going to study about the or we are going to build a mathematical model of, so the mathematical model of the MIS diode, or we can say charge sheet model. Okay, so here we are going to calculate like the total the charge in the semiconductor. Then with the help of that we are going to calculate the ideal the voltage, that is the threshold voltage. Then we are going to study about like the another modified threshold voltage. Okay, now what we'll do, so here we consider already like this charge sheet model will be based on the depletion approximation. It's not only the accurate one in the strong inversion, and also we can say beyond the regions of operation. Now, to start with that, let us begin with the. So, let us begin with the Poisson equation by Poisson equation. So, what is the Poisson equation? States that del D is equal to rho x y z. Consider the equation number 1, where the this D is nothing but electric displacement vector. That is, I can say that D is equal to epsilon s into E. You consider this equation number 2 under the low frequency or static conditions, where in this D equal to epsilon s into E, where the epsilon s is nothing but is the permeability of silicon. Then the capital E is nothing but electric field vector. Then the rho of xyz is nothing but is a total electric charge density. Now,
Sir, 1 minute. Please scroll down the page. Thank you, sir. Done, sir.
Yeah, okay. So now, next, what we'll do, let us substitute the equation number 2 in 1. Substitute equation number 2 in 1. So when you substitute, what we'll get? We'll get as del into epsilon es e is equal to rho of xy z. This is the equation number 3. Then I'll get from here del dot E is equal to rho by epsilon s into xy z. So this you can consider as equation number 4. Now in this, one thing is later we'll see, but now you need to know something like where the E is nothing but minus delta into phi. So later we'll substitute this actually, not now. Okay. So now here where E is nothing but the electric field. Here as I mentioned, the electric field will be in the x-axis. They will not be considering only for the x-axis. They're considering only on the x-axis. So what will happen? The remaining y-axis and z-axis will be 0. So I can say like E will be like we make a test the field electric field I can say in the sense the field vector Ex, Ey and the Ez where Ex only is only Ex only we are going to use. So these two will become as 0. So here I can write as like this like where the E will be dou phi by dou x that is Ex. Then Ey will be dou phi by dou y. Then Ez will be is equal to dou phi dou z. As we know that the y-axis and the z-axis will be 0, only the existing is dou phi by dou x. Okay, so now what we'll do, we'll consider all these things, we'll put together. So if the fringing field at the edges are neglected, then the variations of the electrostatic potential phi can be considered to be only on the x-axis. That is why I mentioned. So only we consider x-axis. So now here we are considered as like Ey is equal to dou rho phi by dou y, then Ez dou phi by dou x. So I can say here these two will be 0. These two will become as 0. Now let us noting that keeping that what we have to do in the sense let us say because both are 0 in the sense what will happen here above the expression will become as row of x of y comma z that will become as row of x actually. So now noting that oh, the row of x will be will write as like this q into p of x minus n of x plus nd of x minus na of x where actually. Now you will consider this is equation number 5. Now what you will do, now the previous equation, the equation number 4 will be transformed as like this or we can substitute the equation number 5 in 4. substitute equation 5 in 4. When I do like that, so what we'll get? So this will be, you can see in the up, like you can see the previous, it is del cross E is right. So now what we can do in the sense here, we can substitute like, let me substitute even E is equal to minus del into 5 also. If I do in that way, I will get us the expression as del into 5, because here E equal to minus del 5. Just I substitute. Let us keep the minus. Okay, later I will take the minus in the right hand side actually. So this will become as del square 5, where del is nothing but the second order term actually. So this will become as d square 5 divided by dx square. Why? Because only x will be remaining. So it will be is equal to this minus I will take to the last. Okay, so now I'm not going to consider this minus. I'm going to just take this minus in the last, or let me take now only better. So for your convenience, so what I will do is this is minus, right? Minus here also. So this minus will be go as right side. So minus rho, not rho, it is q, right? Q by epsilon s into pp, that is p of x. I am writing as p of x. The p of x will be written as pp, that is p suffix p. Then I am writing as n suffix p, and plus writing as nd minus n a. So this will be the expression as number 6. Now, where the where the pp is nothing but mobile hole density, where np is the mobile electron density, then nd is nothing but is the concentration of donor impurities, then Na is the concentration of acceptor impurities. Now here the subscript P, wherever here you can see this subscript P and all, which denotes as like here we are considering the P-type semiconductor. Yeah, we are considering P-type semiconductor. Now what we'll do, let us two carrier points. to carrier densities at point x-axis are related to the first one is intrinsic carrier density, that will be written as Ni, and second is the Fermi potential, that will be given as phi f, then electrostatistical potential, that will be x. So according to the Boltzmann statistics, that is Boltzmann constant will be now by calculating, or let us consider as I initial here, we are taking the point of intrinsic carrier density. The intrinsic carrier density, so let it is take the expression Pp of x will be is equal to, with respect to x axis actually, will be is equal to Ni into e to the power q sigma x minus phi c divided by kt. I think this will be equation number 7. Then similarly for np of x is equal to ni into e to the power q of phi of x minus phi c divided by kt. So these two only I will consider as equation number 7. So here the Fermi potential level phi f, the Fermi potential, the phi f will be corresponds to the Fermi energy level, correspond to the Fermi energy level. So this will be like B is equal to minus q phi f. Now what we'll do, let us discuss, or let us measure the electrostatic potential Now let us calculate or let us measure the potential relative to the potential which corresponds to the Fermi level. Fermi level in the bulk actually. So how we can represent the sense like EI will say the x-axis like so in the bulk in the sense I can go it's say infinite. So the electric field vector actually is equal to infinite I can say. Now the absolute value then the absolute value of phi of x will become as phi of x plus phi of infinity because the work function like in the Fermi level it starts from the x-axis. From the x-axis it doesn't know from where it will start from that value till the infinity. So that is why the combination of both two x and the infinity that only we can consider as. Now let us what we'll do we'll denote the equilibrium hole. Equilibrium hole and electron density. Electron densities in the bulk again. In the bulk. So how can we return that? So let us write that will be like PP0. So as already we written as P of X. So just same thing only I'm writing as PP of 0 will be is equal to PP of infinity because I'm saying as we are taking the infinity one, right? Will be is equal to Ni exp that is exponential e to the power q into phi f minus phi of infinity by kt because this will be like phi f minus phi x means phi x was there no, so I'm going to consider the phi x is nothing but phi f actually, so that's why you written as like this. So similarly we need to write for np0 also. So what will happen in np0? Similarly np0 will be like LB is equal to NT is equal to infinity. Same already written, right? Is equal to infinity. Ni expression e to the power that is phi f minus phi of infinity divided by kt. Now both I'll consider as equation number 7. Now what I need to do, we need to substitute this expression. Let us say whatever we got, like which expression this one, not this 6, 7, the equation number 6. Okay. Substitute this equation number 6 in the equation number, sorry, equation number 6. Okay, supposed to be 7. By mistake, I returned 6. This is 7 actually. This is 7. Then below will be 8 then. Now substitute the equation number 7 and 6. Substitute the equation number 7 in 6. So after that what you will do and multiply both side by 2 into d5 by dx. Now that equation will become as integration from infinity to x 2 into d5 by dx into d square pi by dx square into dx. Just I'm substituting this. Okay, in the left hand side as well as in the right hand side, both the sides. Multiplication integration will be deep. Like we need to integrate from a point deep in the bulk to an arbitrary point. As example, from infinity to x. So this will become as d by dx into d phi by dx the whole square into dx. Now let us rearrange or let us change the interval. Like instead of taking a infinite to x, we're not able to integrate it. So we are going to take from 0 to 5. 0 to 5 we are going to take just we as earlier as I said from the equation number 6. After substitution from the equation number 7, we will get like this. P0 e to the power q phi of x by kt minus np0 e to the power q phi of x by kt plus nd minus na into d phi. You consider this is equation number 8, 9. Now here we need to put some of the conditions or some substitutions we have to make. Okay, so now what we'll do, let us substitute some of the things like at relatively for elevated temperatures, the most of the donors and the acceptors are ionized. So now let us do some simplifications or some of the substitutions we let us make like P P0 is approximately is equal to Na, I can say. Next, we'll say that NP0 is approximately is equal to ND is donor. Again, approximately I can say Ni square by Na. Again, I'll say the NPK, sometimes NP0 can be written as Ni into e to the power minus beta phi d, because if we consider the Boltzmann constant, so this will become in this NP0 is equal to Ni. So again, the NP0 I can write as will be equal to this, like P0 e to the power minus 2 beta phi d. Now what you do, substitute these all the terms. Equation number 9. So when you substitute these things, so the equation will become as d phi by dx will be is equal to, as I mentioned earlier, like, so minus was, I hope you remember that minus. So you need to consider that minus also, minus, like minus, then we'll have like this 2qna divided by epsilon s, then again this root e to the power minus beta phi divided by beta plus phi minus 1 by beta. Substitute, you need to substitute that. Okay, so do the substitution and you will get this. Hmm. Then e to the power beta phi divided by beta minus phi minus 1 by beta. Now, the electric field at the surface, the electric field, the electric field at the surface, that is EF, will be obtained obtained by substituting phi is equal to phi s in the above equation. Which equation? I will say the above equation will be set as equation number 10. So this equation I can say equation number 10. Now what we need to do, we need to find out like to determine the total charge in the semiconductor, that is QS. So now further what you have to do, we have to by using Gauss law. What is the Gauss law states that the QS is equal to epsilon S into ES. So what you need to do, already we are having a ES already. The previous expression, substitute that. So we will get the expression that is minus 2Q epsilon S Na divided by epsilon S, then e to the power minus beta phi S plus beta phi S minus 1 plus e to the power minus 2 beta phi B into e to the power beta phi S minus beta phi S minus 1. Yes, sir. This is nothing but your QS. So I can say this will be the final equation number 11. So now what we need to do, we need to calculate the threshold voltage. That is ultimate aim is that only to find the threshold voltage, because like you may say when you're applying the voltage between the gate, that is the top of the metal, right? Then bottom will be, bulk will be there. There is no direct electricity from the metal to the semiconductor, actually because of intermediate you are having a insulator. So what will happen, like as I mentioned, the threshold voltage, if I say when you apply more and more positive voltages, so like there is a chances of changing the threshold voltage over there. So since the phi of x tends to infinity, as I mentioned, like will be is equal to 0. So now we can say as a part of applied voltage, part of the applied voltage V across the insulator and the remaining across the semiconductor. So that will be given as like V is equal to phi I plus phi s. This is the voltage. The part of the applied voltage V will be across the insulator and the remaining across the fluid. So now where the phi I will be is equal to Qs divided by Ci, and where the Ci will be is equal to epsilon I by d. Now we need to know what is the terms like the Ci. What is the Ci term? The Ci term is nothing but it's a capacitance of the insulator. Capacitance of the insulator. Then what about the epsilon I? The epsilon I is nothing but it's a permittivity of the insulator. Then what about D? The D is nothing but the thickness. We said in the previous initial classes. Thickness of the insulator. Now what you'll do, you substitute those things in this equation. Which equation? You consider the previous one. This is, I will take it as equation number 12. This I will consider as equation number 12. You want to substitute the polygon value over there. So we may get V is equal to, what is the first thing? We'll get as Qs by Ci plus phi s. Again we'll get the V is equal to Qs d by silicon ASI plus phi s. So this I will consider the equation number 12, not 12, it's 13 I. Now by smooth inversion, the phi s will become as twice of phi b. So then the threshold voltage will be defined as VT. The VT, this capital VT is defined as like what is that? The QS, I will write as the strong inversion, right? The strong inversion of QS, the charge of semiconductor into D divided by say, epsilon I plus what is the phi s? Phi s is nothing but 2 times the PV. So this will be your equation number 14. The QS is semiconductor, the charge will be in the strong inversion by strong in the strong inversion. Now R I can write as BT is equal to, this can be written as 2D divided by epsilon I Q epsilon S NU phi B 1 minus e to the power minus 2 beta phi B plus 2 phi B. So this will be this is equation number 15. This is for ideal voltage, ideal threshold voltage. What we'll do, like let us consider, we need to find out ideal threshold voltage, then modified threshold voltage. Sure. So what we'll do, like sometimes, as I say, the work function, the difference earlier in the beginning class we said the work function is zero. That is zero. In particular, particular technique, the work function will decrease finally will never become zero. So it's not become zero in the sense there will be maybe some charges will be present in the insulator or at the insulator in the semiconductor body.
Sir, I
So
think
those
there's some issue in your mic, sir. Often I'm getting weird sounds, sir.
what happened? It's,
Like your sound is getting buffed in the middle you're talking.
is it fine now? Now we are getting properly.
Yes, sir.
Now my audio is audible clearly.
Yes, sir. Yes.
Yes. Okay. Thank you. So as I mentioned in the earlier, like the work function, the phi ms will be zero. So I hope you remember in the beginning class, as I said, the phi ms will be is equal to zero. But if I say practically, the phi ms will not become as zero because there will be some charges will be present uh, in the insulator or at the insulator semiconductor boundary actually. So those are like the mobile ionic charges, the fixed oxide charges, then interface trap charges and the oxide trap charges. Now what we'll do, let us take that one thing we specified when V is equal to zero, work function is equal to zero means we studied about something called as flat band voltage. That is VFB, flat band voltage. That we can call as VFB. What is the VFB in the sense? The VFB will be is equal to phi ms minus qt into d divided by epsilon I. So here, what is the flat band voltage? It defines. So it's nothing but it's a total voltage needed to offset the effect of non-zero work function difference. And the presence of the charge is referred as flat band voltage. Here you can see the phi ms is nothing but a work function. Then what is the qt? So we need to know about the qt actually. This is already we know, right? It's a work function. The work function of metal, and that is the difference, right? Work function metal and the semiconductor. Here, what is qt? The qt is nothing but it's a effective net charge. So effective net charge per unit area. So now this will be your VFB, that is a flat band voltage. I consider as equation number 16. Now what I need to do, so you will get here, if you need to consider even this also, the flat band voltage also we need to consider. So now at the strong inversion, the threshold voltage will make change. So the voltage, the voltage V that must be applied to reach the strong inversion must include the flat band voltage VM as well. So now what will happen? Your equation will become as VT0 I take because with the flat band, right? So we need to add the flat band also. So flat band plus VT because already we know the VT also. Substitute that will get us VFP plus 2D divided by epsilon I, then Q epsilon S NA phi B 1 minus e to the power minus 2 beta phi B plus 2 phi B. So this will be the root. This is nothing but your VT not, I can say. is one of the very important expression. But we need to know here, like now we can say this VFP is nothing but a flat band voltage. The rest of the things are ideal threshold voltage. So now this will be your final expression. So this portion completely will be your ideal voltage or ideal threshold voltage. So ideal threshold voltage plus the flat band voltage will give you the complete threshold voltage. This is about the calculation of threshold voltage.